Alright, so hi there everyone, this is Nikhil, and in today's video we are going to see how you can use MATLAB and ABAQUS to do a simple finite element analysis problem. So this is the problem definition. We have a bar having three different cross sections given by the areas A1, A2 and A3, and they are having a length of 100 mm, and the material is steel having a Young's modulus of 200 GPa, and we are applying a nodal force of 500 newtons at the tip of the bar, and we are fixing the other end of the bar. So our objective is to find the stresses and strains in each section of the bar. So the first step is to discretize the given domain into nodes and elements. So we are naming the nodes 1, 2, 3 and 4, and we are naming the elements 1, 2 and 3, and we are finding the element stiffness matrix. So the area A1 is given by 30 by 30 mm square. So we are converting the mm square into meter square. So that is 900 into 10 power minus 6 meter square. And similarly the area 2 is given by 20 by 20 mm square. So converting that into meter square, we have 400 into 10 power minus 6 meter square. And then followed by the A3, which is 10 by 10 mm. So 10 by 10 mm square will give us 100 into 10 power minus 6 meter square. And the Young's modulus is going to be same for all the three sections, that is 200 GPa, and here the units are important. So here we are converting the gigapascals into pascals, so that will be 200 into 10 power 9 pascals. And then we have L1, L2 and L3, that is the length of the element. So the length of the element is 100 mm, and we are converting that into SI units, so that is going to give you 0.1 meters. And so the element stiffness matrix is given by AE by L into 1 minus 1 minus 1 1. So if you multiply the A1E by L1, it is going to give you 1.8 into 10 power 9, and if you do the calculation for A2E by L2, it is going to give you 0.8 into 10 power 9, and in the last case if you multiply A3E by L3, it is going to give you 0.2 into 10 power 9, and then we have 1 minus 1 minus 1 1 as the matrix. So this is the each individual element stiffness matrices, and now we need to calculate the global stiffness matrix. So to calculate the global stiffness matrix, we are going to assemble them by giving the notation of each displacements. So 1.8 plus 0.8 will give you 2.6, and similarly 0.8 plus 0.2 will give you 1. So those values will get added, and finally we calculated the global stiffness matrix. And now the finite element analysis equation is K into U is equal to F. So we have the element stiffness matrices clubbed into a global stiffness matrix that multiplied with the nodal displacements U1, U2, U3 and U4 is going to give us the nodal forces. So the nodal forces are 0 except for the last one, where we are applying a 500 newtons of force, and we are applying the boundary condition for fixed condition. So U1 is fixed, which means U1 is equal to 0, that is the fixed condition. So the first row and first column will get eliminated. Therefore the global stiffness matrix is going to reduce into 3 by 3, and so you have U2, U3 and U4. So now we will go to the MATLAB. Just search MATLAB online, and click on sign in. and sign in with your ID. After you sign in, it is going to take you to this particular page. Go to the right hand top corner and click on My Account. And click on this particular button here and click on MATLAB. And then finally click on Open MATLAB Online. So it is going to take you to the MATLAB interface. This is how the MATLAB interface is going to look like. I'm going to close this tutorial, and the first thing that you need to do is to click on New Script and start typing the command CLC for clearing it, and give clear. The CLC will clear the command window, and clear will clear the memory for us. And then we have the stiffness matrix, so that it will be K is equal to 10 power 9 asterisk, and now you are going to enter the matrix values, that is 2.6, if you go back here, this is what we are trying to enter, 2.6 minus 0.8, give a space here and enter minus 0.8, and again give a space, and then we have 0, and after you enter the first row, give a semicolon, so that it is going to take the elements of the second row. In the second row we have minus 0.8, give a space, and then we have 1, and then give a space, and then we have minus 0.2, that is minus 0.2, and now the second row is complete. Again give a semicolon, and in the last row we have 0, give a space, and then minus 0.2, give a space, and then we have 0.2. So we have entered all the values of the stiffness matrix. Give a semicolon here, and then we will input the values of the force vector, that is F equal to, we have 0, 0 and 500, so it is 0, and here you have to give the semicolon to enter into the second row. Again we have 0 in the second row, and in the last row we have 500 newtons, and at the end give a semicolon. So K and F are defined. So now we need to compute the displacement vector, that is U. So U is equal to inverse of stiffness matrix multiplied by the force vector. So in order to compute inverse of the matrix, the command in MATLAB is backslash. K backslash will compute the inverse of K, and then you multiply with the F, and so you are computing the displacement vector. And go to the save as and save this file and give this a name. I will give this tutorial code. Don't give any space in the file name because spaces are not allowed, and then click on save, and now you can click on run, and in the command window you can see the output of the program, that is U equal to 1.0 into e power minus 5, that is 10 power minus 5, multiplied by 0.0278, that is u2, and then you have 0.0903 as u3, and then you have 0.3403 as your u4. So we have computed the displacements u2, u3 and u4 using MATLAB, and the next step is to find the strains. The steps for computing the strain E1 is nothing but u2 minus u1 by L1, that is change in the length of the element divided by the original length. So that is going to give you 10 power minus 5 into 0.0278 minus 0 divided by 0.1, that is going to give you 2.78 into 10 power minus 6. Similarly, you can compute the strain in the second element, that is E2. E2 is given by u3 minus u2 by L1, and so the value is 6.25 into 10 power minus 6. And lastly, we have strain in the third element, that is E3, which is given by u4 minus u3 by L1. So instead of giving the L1, L2 and L3, I have given it as L1 only, because the lengths are same for all the three elements, and the strain in the third element is 2.5 into 10 power minus 5. So ideally this should have been L2 and this should have been L3 to get more clarity, but in our case all the three values of lengths are equal, that is 0.1 meters, so that doesn't matter here. But if you have different lengths for each element, you should divide it with the respective lengths. And finally, from strains we can compute the stresses, that is stress in the element 1 is given by S1, that is equal to Young's modulus times the strain. So Young's modulus is 200 into 10 power 9, and so if you multiply it with the strain value, you are going to get the stress, and the value will be in SI units, so that is pascals. So 0.556 megapascals, and similarly the stress in the second element is 1250000 pascals, that is 1.25 megapascals, and stress in the third element S3 is 5 megapascals. So this is how you can compute the stresses using the finite element analysis approach using MATLAB. And now we will verify this result using ABAQUS. So before you go to ABAQUS, you have to model the bar in Fusion 360. You need to create the geometry file. So for that, I will take you to Fusion 360. This is the Fusion 360 interface. If you want to learn Fusion 360, there are separate YouTube playlists which I will share. So I will quickly model the geometry. The first element is having 30 millimeters by 30 millimeters cross section, and I am going to extrude this by a value of 100 mm, that is the length. I will click on OK, and then I will create another sketch here and take a rectangle command, and I will give you the values here, that is 20 millimeters by 20 millimeters. This is for the second element, and the length is again 100 millimeters. And lastly, we will model the third element. So third element cross section is 10 mm by 10 mm. So I am going to extrude this also. So the length is 100 mm. So now we have modeled the given problem. I am going to save this. and ABAQUS reads the geometry in step format. So you need to export the file. Click on export and select the file type as .step, and I am going to save this in this particular folder and click on export. And now our geometry file is exported in step format. And now we need to import this geometry file into ABAQUS. This is the ABAQUS interface. Close this window, and first we need to import the geometry file. Go to file, go to import, and go to part, and then navigate to the directory where you saved the file. And select the file type as step. So this is tutorial file. Click on OK, and it is going to ask you to give a file name. I am not going to change this file name, and I am going to click on OK. And now the geometry is successfully imported into ABAQUS. I will simply save this CAE file. I am going to give this a name. And the first thing that we need to do is to assign the material. So I will right click on the materials tab, and I will click on create and give the name for the material. I am going to give the name as steel. And go to general and click on density, and here give the density of the material, that is 7800 kg per meter cube. You need to give proper units here in SI units. So that is 7800 kg per meter cube. And then go to mechanical properties, elasticity properties, and elastic material, and here give the value of the Young's modulus, that is 200 gigapascals. And the way to input 10 power 9 in ABAQUS is give capital E and followed by 9, and Poisson's ratio for steel is going to be 0.3, and then click on OK. And now we have defined the part and assigned the material, and the next step is to assign the section. Right click on the section and click on create, and select the solid option and homogeneous option, and click on continue, and then select the material here. Automatically it is selecting as steel. Click OK, and then you need to go back to the parts and assign this section here, and right click on the section assignment by expanding the features, and click on create, and select this particular geometry file, and then click on done, and it is going to ask you to assign the section. We have given the section as section 1, and click on OK, and now the section has been assigned. And then finally we need to create a step. Right click on the steps and click on create, and we are performing a static analysis. So click on static general and click on continue, and leave everything as default, and click on OK. Now we have created an initial step, and I am going to save this file for safe side. And now you need to apply the loads and boundary conditions. So I will right click on the loads and click on create, Okay, it is saying part must be instanced or a reference point. Okay, let me check that. So here I will try to assign the mesh. So we have assigned the part, we have assigned the material, we have assigned the sections, we have assigned the steps, and now the next point is to mesh the geometry. I will click on right click on the mesh, and now you need to give a seed value. So I will give a seed value of 5 and click on OK, and now you can see the geometry has been discretized. If you want a finer mesh, you can reduce the seed value. Let's say I will give a value of 1, and now you can see the mesh is more finer, but it is going to increase the simulation time. So I am going to increase this back to 5 and click on OK, and then I am going to go to mesh and click on controls and select the tetrahedral mesh and click on OK, and then lastly I am going to go to the mesh again and click on part, and it is going to ask you OK to mesh the part. Click on yes, and we have generated our mesh successfully in ABAQUS. You can see here it is a tetragonal mesh. So our domain has been discretized into tetrahedrons. So now we are going to assign the loads. So here in ABAQUS you cannot directly give a force, you can only give the pressure load. So you need to convert the force load into a pressure load. The value of force is 500 newtons, and if you divide it with the area, you are going to give a value of 5 into 10 power 6 pascals. I will go to loads and I will click on create. So I missed one step. So here you need to assign part to the assembly. So ABAQUS is going to treat each problem as an assembly. So you need to assign an instance to the assembly. Right click on the instance and click on create and select the part and click on OK. And now you can assign the loads, and it is going to be a pressure load. Click on pressure and click on continue, and it is going to ask you select the face. So zoom in and select this particular face and click on done, and here it is going to give the interface where you can enter the value of the force or the pressure, that is 5 multiplied by 10 power 6. You are entering in pascals, and if you click on OK, it is going to give the pressure load towards the geometry, but our force is acting away from the geometry. So for that, again click on create, expand the load and edit this and give a minus sign here and click on OK, and now you can see that the pressure load is acting outside of the geometry as defined in our problem statement. And now I am going to assign the boundary conditions, that is BCs. Click on create, right click on the boundary condition and click on create. and here we are going to assign the fixed condition to the other face, and in ABAQUS that is going to be called as Encastre. So we are going to apply the Encastre feature. Click on continue by clicking on the Encastre, and it is going to ask you to select the face. So for that, select this particular rotate view and rotate the view using the mouse, and select this particular face and click on done, and it is going to ask you to select the option. The last one is Encastre, where all the three displacements and all the three rotations are set to 0. Click on OK. And now we are good to go to submit the job. So expand the analysis part here by clicking on the small plus icon, and right click on the job and click on create, and give the job a name. I will give this as job 2, and I will click on continue and leave all the settings as default and click on OK, and expand this particular job. And now we are going to see job 2 here. Right click on the job 2 and click on submit. So the job is running in the background. Wait for some time. So it says the job is completed successfully. Right click on this particular job and go to results, and you can see the results. If you click on the deformed shape, you can see that the geometry is expanded or extended due to the load. And if you click on the contours, you can see the contours of the bar having the three elements. And now if you want to measure the stress in each of these sections, you need to go to tools and click on query, and then click on probe values. And now if you zoom in, the stress in this particular region is going to be giving me 5 into 10 power 6 value here. If you see part instance, element ID, type, attached nodes, and then you have stress in von Mises. So it is showing me 5 e power plus 06, that is 5 into 10 power 6. So from MATLAB we computed these values, and from ABAQUS we have a 5 into 10 power 6 value. And if you probe in the second section, it is giving me a value of 1.25. You can see the value 1.25 into 10 power 6. So that is what I typed here. And if you see the probe in the third section, or that is the first section from left to right, it is showing me a value of 555879. So roughly the stress in each of these nodes is in the order of 55500. So that is what I have entered here. So you can see that the values from ABAQUS, the stress values from ABAQUS and the stress values from our finite element method are matching correspondingly. So we can verify the results here, and in this manner we can find out the stresses either using MATLAB or using the ABAQUS. And if you have any questions, please let me know in the comments and I will be happy to help you.